Hello everyone, this is Professor Namrata. Welcome to the video lecture for the course Wireless Cellular and LTE-4G Broadband. In this session, we'll discuss some topics relating to overview and channel structure of long-term evolution. The first topic we are going to discuss is about overview of the LTE radio interface. Second topic is design principles of long-term evolution. Third topic is network architecture. So we'll start with the first topic, that is overview of the LTE radio interface. The radio interface of a wireless network is the interface between the mobile terminal and the base station. In case of long-term evolution, it is located between the radio access network, EUT-RAN, and the user equipment. UT-RAN for the 3G systems has two logical entities, the node B, that is the radio base station, and the radio network controller. EUT-RAN network architecture is simpler and flatter. It is composed of only one logical node, that is the evolved node B, eNode B. Compared to the traditional node B, the eNode B supports additional features such as radio resource control, admission control, and mobility management, which were originally contained in the radio network controller. This simpler architecture simplifies the network operation and allows for higher throughput and lower latency over the radio interface. The LTE radio interface aims for a long-term evolution, so it is designed with the clean state approach as opposed to high-speed packet access, which was designed as an add-on to UMTS in order to increase throughput of packet switch services. The second topic is regarding the design principles of long-term evolution. As we know that the long-term evolution was designed primarily for high-speed data services. It is a packet switch network from end to end and has no support for circuit switch services. The basic design principles for designing the LTE specifications include network architecture, data rate and latency, performance requirements, and this will come across spectrum efficiency, mobility, coverage, and MVMS service. The fourth one, it is radio resource management, deployment scenario, and coexistence with 3G networks, flexibility of spectrum, and deployment. The seventh one, it is interoperability with 3G and 2G networks. We'll see one by one. The first one, it is the network architecture. Unlike 3G networks, LTE was designed to support packet switch network, packet switch traffic with support for various QoS classes of service. The LTE radio access network, EUT-RAN, was designed to have the minimum number of interfaces, that is, the minimum number of network elements. The second one, it is data rate and latency. The design target for downlink and uplink peak data rates for long-term evolution are 100 Mbps and 50 Mbps when operating at the 20 MHz frequency division duplex channel size. And the latency, that is the one-way latency in the user plane is 5 milliseconds in an unloaded network. For the control plane latency, the transition time from a CAM state to an active state is less than 100 milliseconds. The third design principle is the performance requirement. The target performance requirement for LTE are specified in terms of spectrum efficiency, mobility, coverage, and MVMS service. The first one is the spectrum efficiency, that is the average downlink user data rate and the spectral efficiency target is 3 to 4 times that of the high-speed downlink packet access network. Whereas in the uplink, the average user data rate and spectrum efficiency target is 2 to 3 times that of the baseline high-speed uplink packet access network. Now coming to mobility, the mobility requirement for long-term evolution is to be able to support handoff or mobility at different terminal speeds. The maximum performance is expected for the lower terminal speeds of 0 to 15 km per hour with minor degradation in performance. At higher mobile speeds up to 120 km per hour. And the third one, it is the coverage. For the cell coverage, the target should be met up to 5 km. MBMS service, that is multimedia broadcast and multicast service. That is, the LT should also provide enhanced support for the MBMS service as compared to UTRA operation. And the fourth design principle is radio resource management. The radio resource management requires cover various aspects such as enhanced support for end-to-end quality of service, efficient support for transmission of higher layers, and support for load sharing, balancing, and policy management enforcement across different access technologies. The fifth design principle is deployment scenario and coexistence with teaching. The first one is its standalone deployment scenario, and the second is integrating with existing UTRAN or GRAN deployment scenario. At a high level, the LT shall support these two scenarios. In the standalone deployment scenario, the LT deploys either with no previous network deployed in the area or both no requirement for internet interworking with the existing UTRAN or GRAN networks. Integrating with existing UTRAN or GRAN deployment scenario where the operator already has either a UTRAN or GRAN deployment scenario where the operator already has either a UTRAN or GRAN network deployed with full or partial coverage in the same geographical area. The sixth one, it is flexibility of spectrum and deployment. LTE was designed to be operable under a wide variety of spectrum scenarios, including its ability to coexist and share spectrum with existing 3G technologies. LTE was designed to have a scalable bandwidth from 1.4 MHz to 20 MHz. And LTE was also designed to operate in both frequency division duplex and time division duplex modes. The seventh one, it is interoperability with 3G and 2G networks. Multi-mode long-term evolution terminals with support UTRAN or GRAN operation should be able to support measurement of and handover from and to both 3GPP UTRAN and 3GPP GRAN system with acceptable terminal complexity and network performance. Okay, so the next topic we are going to discuss is about the long-term evolution network architecture. This is the diagram. The entire long-term network architecture is composed of radio access network, that is EUTRAN, and a port network. And these are the main components of the EUTRAN and EPC. These are listed here based on the diagram. In this, for the first one is the user equipment, Node B, MME, serving gateway, packet data network gateway, S1 and X2 interface, policy and charging rules function, home subscriber server, serving GPRS support node. All these components are shown in this architecture, that is EUTRAN and EPC. We'll see one by one. The first component, it is the user equipment. User equipment, it is also called mobile terminal. It is an access device for user. It provides measurements that indicate channel conditions to the network. The second component, it is Node B. It is also called base station. It interfaces user equipment to EPC and is the first point of contact for the user equipment. The Node B is the only logical node in the EUTRAN. So it includes some functions. The functions such as radio bearer management, uplink and downlink dynamic radio resource management, data packet scheduling, mobility management. The third component, it is regarding the mobility management entity, MM. This MME is similar in function to the control plane of legacy serving GPRS support node, SGSN. The function is it manages mobility aspects such as gateway selection and tracking area list management. The next component, it is based on the serving gateway. It terminates the interface toward the EUT-RAN and routes data packets between EUT-RAN and EPC, the serving gateway. And it performs local mobility anchor point for inter-eNode B handovers and also provides an anchor for inter-3GPP mobility. The serving gateway and the MME may be implemented in one physical node or separate physical nodes. The other responsibilities include lawful intercept, charging, and some policy enforcement. The next component, it is PDN-GW, that is Packet Data Network Gateway. It terminates the SGI interface toward the packet data network. It routes data packets between the EPC and the external packet data network and is a key node for policy enforcement and charging data collection. It also provides the anchor point for mobility with non-3GPP accesses. The external PDN can be any kind of IP network as well as the IP multimedia subsystem domain. The PDN gateway and the serving gateway may be implemented in one physical node or separated physical nodes. The next component, it is the S1 interface. The S1 interface is the interface that separates EUT-RAN and the EPC. EUT-RAN and the EPC. It is split into two parts, that is S1U and S1MMU. The S1U carries traffic data between the eNode B and a serving gateway. The S1MMU, it is a signaling only interface between the eNode B and the MMU. The next component, it is the X2 interface. The X2 interface is the interface between eNode Bs. It always exists between eNode Bs that need to communicate with each other. For example, for support of handover, it consisting of two parts, that is X2C and X2. It is the control plane interface between eNode Bs. The other is, it is the user plane interface between eNode Bs. The next component, it is policy and charging rules function. This component, it is for the policy and charging control. The next component, it is HSS, that is Home Subscriber Server. It is responsible for the service authorization and user authentication. The last component, it is SGSN. It is for controlling packet sessions and managing the mobility of user equipment for GPRS networks. Thank you for watching this video.